Hello everyone, this is Ignacio Ruiz. In this video, we're going to talk about the P&L Attribution test. In particular, we're going to discuss how we can comply to such a test within the FRTB framework with some very specific machine learning techniques. I hope you enjoy it. Before we go into the video itself, I'm going to summarize for you what we are discussing when, so that you can skip to that part of the video if you cannot watch the whole thing. First, in around minute 1, right after this, we're going to talk about the problem of FRTB that we are going to be tackling in this video. Then, in around minute 7, we're going to talk about the methodology of smart sampling machine learning. Then, in around minute 24, we're going to see some numerical results of what can be achieved with actual real live results. And then finally, in around minute 32, we'll go through some conclusions and key takeaways. So first of all, let's frame the problem so that we are all on the same page. The P&L attribution test compares the front office prices with the risk engine prices. Typically, the risk engine prices are called the risk theoretical P&L, RTPL, and the front office prices are the high HPL or hypothetical P&L. The P&L attribution test consists in two tests: the Spearman correlation and the Kolmogorov-Smirnov or KS statistics. For each of them, there are some borders between a green, an amber, and a red zone, depending on the score that you get. When you compute these two numbers using the risk engine pricing models with the front office pricing models, you always want, obviously, to fall in the green zone, because in that way, the model goes through and there is no downside on the capital side of your FRTB calculation through the models approach. What is the challenge that we have, like from a big perspective? In a typical expected shortfall calculation for FRTB, we have a number of scenarios, let's say 1,000 scenarios, and then we pass these scenarios to what we could call like a pricing engine framework, in which you have on one hand the pricing methods, the pricing models, and on the other hand the portfolio of the desk in which you want to evaluate the expected shortfall. And with this, so you have to evaluate this portfolio on each of these scenarios using these pricing models, and this arrives to a pricing vector, which in this example, again, is 1,000 values. Once you have these 1,000 values, then you compute the expected shortfall and all the metrics that you may find appropriate. What are the key elements here, or the key solutions that we can apply to this type of framework? The first thing, as I already mentioned before, is that you can use directly the front office pricing library, what I call brute force, in order to price your portfolio in the expected shortfall calculation. The good thing of this approach is that it is, by construction, 100% accurate, therefore fully regulatory compliant. What is the downside? That it is slow and expensive to compute. Alternative to this, we have classical approximations like GRICS or pricing grids, in which basically in GRICS we use a Taylor expansion. In pricing grids, what we do is we have some sort of standard, simple interpolation method. The good thing of this type of approach is that it is quick to evaluate and cheap to generate. Well, the GRICS is cheap to generate, but the pricing grids, usually they are not so cheap to generate. So I put this note here. Also, a downside of this technique is that accuracy tends to be poor, and because of that, tends to be disliked by regulators. And in fact, you can argue that the reason why the P&L attribution test was put in place by the regulators was because they wanted banks to go away from poor approximators. A third solution to this is basically to get the front office pricing library and to build a trimmed down version of that front office pricing library, in which you actually control the accuracy, you decrease the accuracy, but at the same time it's faster to run. The challenge with this type of framework is that it could be faster to run, but usually it's not super fast. And also a key challenge is that you have to do this for each pricing model that you are going to be using in the desk in which you want to compute the expected shortfall. And this framework overall is quite difficult and it's mostly expensive to run. Finally, we can think of some classical machine learning methods. The good thing of classical machine learning methods is that they are very flexible, and also an AI model always provides an answer. Of course, the challenge is that the calibration to a good level of accuracy is very slow to converge, but this meaning that you need lots of points in order to get to the final result that is good enough for the P&L attribution test. And also, because of that, it is very expensive to train because you need a huge amount of sampling. And also, a downside of this type of methods is that they tend to be a black box, and regulators don't like that. It is a method that, if it delivers an answer that we don't understand, that is a bit strange, we really don't know why. It is a method that is not meant to be fully explainable, but to give an answer that in average tends to be good. That's the idea. But if it provides some straight answers, it is difficult to know why. And regulators don't tend to like this type of black box framework or idea. So in a perfect world, how would the pricing revaluation framework would be? We want it to be accurate enough for the P&L attribution test in a stable manner, of course. We want it to be fast to price. We want it to be quick and cheap to calibrate. We want it to be fully explainable, that is, no black boxes. And finally, the whole framework should be economic to run. That's what we're looking for here. All right, let's talk now a little bit about the methodology. As you can imagine, I can only cover so much in this presentation. If you want details, you can go to our book, but I want to cover here at least the basics of what we are doing here. The setting is the following. We have a number of scenarios that are typically produced by the market risk engine. In this case, in this example, 1,000 scenarios. We want to now get the portfolio and price it in all 1,000 scenarios. So if we do this using what I discussed before as the brute force approach, what we're going to do is we're going to price. We're going to do a pricing job in each of the scenarios to arrive to the 1,000 values that we have here on the right. So we produce a P&L vector with all the 1,000 prices that we're looking for. Now, instead of doing this, we're going to be doing the following. First, we're going to read from these 1,000 scenarios, and we are going to create a number of smart scenarios, Chebyshev scenarios. And in a minute, I'm going to explain how we obtain this. The key idea is that this number here has to be much smaller than this. Why? Because once we have this, in this case, 50 scenarios, we're going to price the portfolio in those 50 scenarios. So it is 50 pricing jobs instead of the 1,000 jobs that we had here before. Once we have these 50 values, then we're going to pass it through the AI machine learning algorithm, and we're going to calibrate a function that then we are going to evaluate in all the 1,000 scenarios to produce a P&L vector of 1,000 values. The idea here is that this is the right thing to do, as long as, first of all, this method is efficient to calibrate. Secondly, it is ultra fast to evaluate. And third, obviously, there is good pricing accuracy between this vector and this other vector. That's what we are going into. The question here now is, how do we generate all these paths? So there are two clear candidates for this. One is DNNs, and the other one is Chebyshev tensors. Let me talk a little bit about Chebyshev tensors now. Chebyshev tensors, they are rooted in the following, they're grounded in the following theorem. If we have a function that has some properties that usually pricing functions do have, and then we approximate it with a Chebyshev tensor with n points, the distance between those two functions in the supreme norm, that is the maximum error between those two functions, converges exponentially fast with the number of points. This is very important because this exponential convergence means in practice two things. First of all, that very few sampling points are needed to approximate the function f with high accuracy, which is something that we want. Why? Because originally this f is heavy, is expensive to compute, so we want to compute it as little as possible. If we have exponential convergence, that means very few points are needed to have high accuracy because we are sampling the function in some very specific points that unleash this exponential convergence. Secondly, something also quite interesting is that if we want more precision, if we want more accuracy for whatever reason, the Chebyshev theory gives us a prescribed way to achieve it. So we don't need to try and error things. We know exactly how to increase the number of points to exponentially fast increase the accuracy. Okay, so this is the grounds, the basis of Chebyshev tensors that we are going to leverage from. Let me show you with this example the power of this exponential convergence. Let's say that we are doing the typical spot surface in which we have a grid of points, typically equidistant, and then what we do is we interpolate in between these points, typically using linear interpolation or some sort of a spline, something like that. So here on the right-hand side, we have the number of sampling points, and here on the vertical, we have the maximum error. You can see how the blue line is the error of this framework here, which you can see how as we increase the number of points, of course, it gets better, but it really flattens out. Note that the error is in log scale. It flattens out. That is, we hardly get any better as we increase the number of points here. However, if all we do is move the same number of points, but we move them to the Chebyshev points, which are the ones that as you see in the screen here now, we move them to the Chebyshev grid, and now we use a Chebyshev tensor in order to extend the function in between the points. We have the orange line. That is, we have increased. Look, if we are happy here with a resolution with a precision of 10 to the minus 1 with 256 points, by only moving the points to the Chebyshev grid, we achieve 10 to the minus 7 precision. So in practice, perfect pricing. Only by moving the points from an equidistant grid to a Chebyshev grid. You can say, okay, well, I am happy with this level of precision. So what we can do is we can actually, if you use the Chebyshev tensor framework, we can actually obtain the same level of accuracy with only around 25 points. So this example illustrates the power of the Chebyshev tensors. If we sample the function on those points, we obtain much higher accuracy or the same accuracy at a lower effort, at a substantial lower effort. Because of that, Chebyshev tensors are great frameworks to approximate functions. The best property is the one that we just discussed, which is that very little sampling gives very high accuracy. But they have a fundamental problem or limitation more than problem, which is that they have a strong curse of dimensionality. What do we mean by that? We mean by that as we increase the dimensionality of the input domain of the function, the number of points, the number of sampling points, the number of Chebyshev points increases exponentially fast, and that is not ideal. Let me give you an example. Let's say that we have a one-dimensional tensor, so with 10 points. So we just have 10 points in the tensor. Excellent. 2 dimensions, we are going to have 10 by 10, that is 100 points. 3 dimensions, 10 by 10 by 10, that is 1,000 points. And then 4 dimensions, 10,000 points, etc., etc. So that the number of points that we have in which we have to sample the function, in principle, if we use a full Chebyshev tensor, grows exponentially fast with the dimensionality. And that is suboptimal. This means that this type of tensors are only good when the input domain of the function is of low dimension. In fact, when it's in low dimension, it is the best approximation framework you can imagine. When it's higher dimensions, then it's also really good, but we need to do something to it. And there are two things that we can do here. One of them is Chebyshev tensors in TT format, and the other one is Chebyshev tensor sliders. Let's go into each of them a little bit. So let's talk now a little bit about Chebyshev tensors in TT format. On one hand, we have full Chebyshev tensors that, as we have seen, they have ultra-fast convergence, this exponential convergence property that we discussed before, but also they have a limitation, which is a curse of dimensionality, a strong curse of dimensionality. On the other hand, we have DNNs. Let's talk about DNNs for a second. In a DNN, you explore the function randomly, in random points. This is in contrast to a Chebyshev tensor in which you have to explore the function on a prescribed set of points, the Chebyshev points. In a DNN, you do this randomly. You have a lot of freedom how to do that. And then once you have that, you calibrate a computational framework like this to minimize the error in these points. And this computational framework, the DNN itself, it has also a lot of flexibility in the sense that you can have as many layers as you want, lots of cells in each layer, or only a few cells if you prefer. You can have different activation functions. So in general, DNN, the positive side that it has is that there is a very flexible approximation framework. The downside that it has is that it converges very slowly. What do we mean by that? Is that the output of the DNN, in principle, the more points you give to it, the better the DNN learns, therefore the more accurate it gets in terms of the quality of the output. However, the reality is that the convergence of the quality of the output, of the accuracy, as you increase the number of points in the DNN, it is very slow to the point that usually there is a moment in which you can give more points to the DNN, more sampling points, but the DNN hardly gets any better at uh, learning the function that it's trying to learn. This is in contrast to Chebyshev tensors that, as we have seen, is the opposite. You always have a way to make it better. Now, what we are going to create now is a hybrid between these two worlds. We are going to explore the function in random points, like in a DNN, but there are going to be random Chebyshev points, and that is represented by the red dots here. So we are going to explore the function in a subset of the Chebyshev tensor, the full Chebyshev tensor, that is randomly distributed in the Chebyshev tensor. We're going to get these points, the red points in the graph, and then we are going to split them into a training set and a testing set, again, inheriting ideas from DNNs. And we are going to calibrate these points. No, sorry, before that, we are going to express the Chebyshev tensor in a very particular format called TT format, the tensor trained format. And then with these sampling points that we have here, the red ones in the graph, we're going to calibrate the Chebyshev tensor in TT format towards the full Chebyshev tensor so that it gets pushed towards the exponential convergence that this one has. On that way, we create an approximation framework that has the best of both worlds. On one hand, it is highly flexible like DNNs. On the other hand, it inherits the exponential ultra-fast convergence of the full Chebyshev tensor. Let me show you how the power of this technique. We published this paper in Wilmot magazine in which we replicated these other papers that what they were doing, they were approximating a Bergomi RAF volatility model using DNNs. And we did exactly the same as these guys did so that we could compare apples with apples. And let me give you a summary of what we obtained. In terms of accuracy, the brute force, so the RAF Bergomi, the Bergomi RAF volatility model is a Monte Carlo simulation by itself. So it had a precision of around 0.5%. The Chebyshev Tensor approach has a precision of around 0.6%, so more or less the same, and DNN around 1%, so similar as well. When we were evaluating the function, of course, this one was taking a lot of time. Its evaluation was 2.6 seconds, a lot. Chebyshev Tensor 10 to the minus 5 seconds, so a massive improvement, and DNN's 10 to the minus 4 reportedly. So more or less Chebyshev Tensor, again, a bit better, but 10 to the minus 4, 10 to the minus 5, both are really good. Now, the interesting bit was when we compare the effort that it required to calibrate the AI model, so the Chebyshev Tensor or the DNN. For the Chebyshev Tensor, we needed between 15 and 20,000 sampling points to calibrate it to this level of precision. However, for the DNN, we needed 3.5, well, those papers reported that we needed between 3.5 and 7 million calls. So we're talking about a completely different order of magnitude. We're talking about 15 CPU hours here to calibrate this versus 212 CPU days here. So here you can see the power of Chebyshev Tensor, the power of smart sampling that Chebyshev Tensors provide. It really makes the calibrating effort of your machine learning function much, much more efficient. In this example, 2 orders of magnitude. Now, let's move on now to the other version that I discussed before in order to manage the cost of dimensionality, which is sliders of Chebyshev tensors. Again, we have full Chebyshev tensors on one hand that are super fast to converge. Importantly, in this context, they converge on a wide domain, so they don't only converge like Taylor expansion. I'll say in a minute why I mentioned Taylor expansion now. They don't converge only around the center of the approximation, but in a wide domain, and they converge in the whole domain exponentially fast. As a downside, cost of dimensionality. Now, we have also Taylor expansions. Taylor expansions, the good things about them is that they are very well understood. However, they only converge locally around the center of the approximation, and also they converge quite slowly. So again, Chebyshev tensors is a hybrid between these two because we're going to do the following. Let's imagine, now I've shaded this out because the idea that I want to get across is, let's imagine, for the sake of argument, for the sake of an example, let's say that we have a function that has the derivative, a pricing function, that the derivative of the price with respect to the time to maturity and also to the volatility is negligible, as usually that's the case. So usually what we do in the financial industry is we neglect that Greek, we neglect that Taylor, part of the Taylor expansion. We're going to do the same thing here. From the full Chebyshev tensor, we are going to chop off some parts that we know that are non-relevant. And when we do that, the exponential the cost of dimensionality that is exponentially fast, we can manage it very, very strongly, to the point that in many cases, as we'll see later in the results, something that is exponentially fast becomes linear in terms of is linearly fast, in the sense that a number of points that grows exponentially now grows only linearly. This is a way that we have that is also quite strong to manage the cost of dimensionality. Let's look now into some numerical results. For us to test this, what we did is we were working with this bank, and we used a portfolio of interest rate swaps, another portfolio of swaptions. And the goal of this test was to see if we could decrease the computational burden for at least 50%, and also if we could compute the expected shortfall with a precision of at least 10%. Let's look at the results. For the portfolio of swaps, the portfolio had 635 trades, 335 positions. We were given 3,131 scenarios in which we had to price the portfolio. And what we did is, through the Chebyshev tensor approach, we computed 51 Chebyshev scenarios, the smart scenarios. And then from these scenarios, we priced it only 51 times. And then we used the Chebyshev tensor to compute the over 3,000 prices. Here on the left, you can see the results in the sense of the horizontal axis is the brute force price, so the price using the front office model, and the vertical axis is the price using the Chebyshev approach. And of course, if these two prices are identical, we'll see all the dots in a straight line. And as you can see, they are really very close to a straight line. Here on the right, you have the blue bar is the expected shortfall using, again, brute force, the front office pricing models directly. And the red dot is the expected shortfall using the Chebyshev smart sampling approach. And again, as you can see, they are right on top of each other. In fact, in this case, is less than 1%, so 0.02% error in the expected shortfall. And we also measure the P&L attribution test numbers, and as you can see, both of them were in the green zone. And we were able to achieve this by pricing the portfolio only in 51 scenarios, the Chebyshev smart scenarios that I discussed before. Now, looking at the options, again, it was over 400 positions. We were given over 3,000 scenarios in which to price this. We generated, in this case, is non-linear, so we need a few more than the 50 that we used before, or 51. We use 151 scenarios, the smart 151 Chebyshev smart scenarios, and then from this, using a Chebyshev tensor, we extended the price everywhere. And as you can see here, the price is very close to a straight line with a few exceptions, of course. And then when we computed the expected shortfall, the blue bar and the red dot are right on top of each other. The error is very small, as you can expect from the plot. And also we measured the P&L attribution test, and as you can see, they were both very, very good. Both of them in the green zone. And really, this is what matters, because what regulators are going to let you use a pricing framework that is different from front office, as long as you pass the P&L attribution test. And this is what we did here quite nicely. In terms of, and then we went to the options, but instead of here we use 10 days liquidity horizon, here now we use 60 days liquidity horizon. We do that calculation. And for us to do that, we use the same Chebyshev tensors that we calibrated here. So in this case, the number of evaluations via Chebyshev was 0. Why? Because we were reusing the Chebyshev tensors that we calibrated before. And as you can see, it was a very nice result, or more or less in a straight line, nice accuracy in the expected shortfall, and always well within the green zone for the Spearman correlation and Kolmogorov-Smirnov test. This was one bank, and then another bank. Also, we did a test with them, and in this case, it was a broader portfolio. We have interest rate swaps, FX forwards, and quite interesting, quite a few exotics, FX stars, and equity autocallables. In this case, we also wanted to get a computational performance of at least an improvement of at least 50%. And now in this case, they mentioned that they just wanted to look at the P&L attribution test. That's all they wanted to look, because that's really what regulators are going to check. Looking at the swaps, now we are not surprised about this. I can imagine all the results are more or less in a straight line. And also now we are plotting here the P&L attribution test results. These two this part of the plot is for the correlation test. This is the green zone, and as you can see, and this is the amber zone. And as you can see, the red dot that represents the actual value from the test is well in the green zone. And here at the bottom, you have the Kolmogorov-Smirnov test, the green zone and the amber zone. And as you can see, again, is well within the green zone. So in this case, the number of scenarios were 500. So we priced the portfolio of 2,700 trades. It was a hedged portfolio, by the way, the same as the other one, by the way. All these portfolios are hedged. So we priced them, instead of 500 times, we priced them only 21 times. And with this, we were able to reproduce the the P&Ls very well and pass the P&L attribution test metrics quite nicely. Now, for the FX swap, something similar. In this case, the portfolio had around 2,000 positions. We were given 1,000 scenarios. We calibrated the Chebyshev tensor using 56 smart Chebyshev scenarios. And with this, we were able to obtain very high accuracy. You can see this is more or less a straight line. The P&L attribution test is well in the green zone here and here as well. Going to the next one, FX forwards. Now, I'm sure you can expect this. This is a very simple vanilla product. So everything has super straight line and everything in the P&L attribution test well in the green zone. Going to the more interesting stuff, FX stuffs. Again, the prices are nicely in a straight line. From the 1,500 scenarios in which if we did this brute force, we had to price the portfolio. We only priced it in 71 smart Chebyshev scenarios. And with this information, we could reproduce all the prices. And the P&L attribution tests were well in the green zone as well. And finally, for the equity autocallables, again, we were given 1,500 scenarios. We priced it in only 80 scenarios. And from this information, we extended the price everywhere with the Chebyshev tensor. And we were well within the green zone of the P&L attribution test again. Okay, so let's wrap up now with a few takeaways. On one hand, we have seen how we are able to replicate pricing functions using the smart sampling that Chebyshev tensors provide, so that very few sampling points are needed to get very high accuracy, which is what is required for the P&L attribution test. As a result, we can comply with the P&L attribution test with this type of machine learning techniques. We can do that at a substantial reduced cost compared to a standard implementation of FRTB-IMA. And third, without any black boxes in the algorithm, because these Chebyshev tensors have analytical formulas in them, so that everything is explainable and everything is well understood. This is what the smart sampling that Chebyshev tensors deliver for us to use, for example, in the context of FRTB. So finally, if you want to implement this, usually the way I suggest that it's implemented is that if this is the red box illustrates a bank's infrastructure, so you need to build the following setup. We need a pricing. We have a number of pricing scenarios, the scenarios for the FRTB calculation and the portfolio. We pass this to this that I call the smart sampling machine learning box. And this, with this information, this box creates the Chebyshev smart scenarios that are sent back to the pricing engine. It returns the prices, and then with these values, we calibrate the tensor, and we evaluate the tensor in all original scenarios so that we have the pricing vector and then expected shortfall and all other downstream processes. So note that, of course, this is done. Let me emphasize it again. We started with typically 1,000 scenarios, but we only have to price it 50 times now. And the bulk of this calculation, it is actually here. All this part of the calculation is super efficient and super fast. So this is something that I have partnered with a number of vendors, of technology providers. So if you want to test this, get in contact with us. Or if you want to implement this yourself in your own systems, you can do that yourself. Just keep in mind that this is a proprietary algorithm subject to a patent. So you have to talk to us to do that, but we are more than happy to discuss it with you. So as I said, feel free to contact us. I will be looking forward to listen to your comments and to your views. And yeah, you can go to our website where there is a contact form. And that is a very nice way for you to reach us. So finally, I'm going to leave this disclaimer here for you to read for the next few seconds. I hope you enjoyed the video, and thank you very much.